Hi everyone. In this lecture, I want to continue on two-port circuit modeling. So in previous lectures, you saw that we can model a two-port circuit by Z matrix or Y matrix. Today, I want to show you how we can model a two-port circuit by A or B matrix. So in A and B matrix, our selection for independent variable is different than what we chose previously for Z and Y. We call this A and B matrix as transmission matrices. In transmission matrices, our focus is either on input or output. So let me draw the two-port circuit one more time here. So here I have V1 and I1. And then on the other terminal, I have V2. And I have I2, but for transmission matrices, instead of I2 in this form, I prefer to focus on minus I2. The reason is that I want to have a block which has an input and then an output. So I'm looking at this two-port circuit in form of a control block. So it has input and output. So I can focus on input variable or output variable. So because I'm looking at this circuit in form of a control system or a system that has two parameter as input and two parameter as output parameter, then I prefer to show the current going out, which is then I have to consider a negative sign. Okay, so for A, I'm focusing on output parameter as my independent parameter, and for B, I'm focusing on input parameter to be my independent variable. Okay, so for A, which I have my output parameter as independent one, then I can describe V1 and I1, which are my dependent variable in terms of my independent one. So this is how it looks like. A11 multiplied by V2 minus A12 multiplied by I2, and then A21 multiplied by V2 minus A22 multiplied by I2. So as you can see, my output parameter, I2 and V2, are my independent variable, and my input variable are the dependent one, which can be described based on the independent variable. Now for B, I'm focusing on the opposite parameter. So this time I would like to describe V2 and I2 in terms of V1 and I1. So I'm going to have B parameter, so B11 multiplied by V1 minus B12 multiplied by I1, and then I2 will be described by B21 and B22 when they're multiplied by V1 and I1. So as you can see, this time my dependent parameters are the output parameter, and my independent one are the input parameter. Now, in order to see how we can find this parameter, I'm going to focus on each one separately. Let's start with A. For A, so for A matrix, in order to find A11, what do I need? In order to find A11, I have to make sure that I2 is equal to 0. So then V1 divided by V2 when I2 is equal to 0 is going to be A11. What is A21? For A21, I have to make sure that I2 is 0 again. And this time, A21 is going to be I1 divided by V2. I have still the same constraint of I2 equal to 0. Okay, I have two more parameters to find. I need to know how I can calculate my A12 and A22. Let's go back to the equation one more time. For A12, I need to get rid of this term, so V2 should be 0. Same thing for A22. I need to get rid of this V2. So for both of them, for A12 and A22, V2 should be 0. I'm going to write the constraint first here. So V2 is 0 here, and same thing here. And now let's see what I have. A12 is going to be minus V1 over I2. And A22 is minus I1 over I2. Okay, so these are four equations that you need to work with in order to find your A matrix. Now, remember that you have to solve your circuit in two different scenarios. So you have to solve it when the second terminal is open circuited. So I2 equal to 0 means that terminal 2 is open circuit. And the second scenario has V2 equal to 0. So it means that your terminal 2 this time needs to be short circuited. So for A12 and A22, you need to have short circuited terminal at your output. So your terminal 2 needs to be short circuited. So for A matrix, your output terminal needs to be short circuited in order to find these two parameters, and the next time you have to make it open circuited for these two parameters. Now let's find the equation for B matrix as well, and then we can look at a couple of examples. So for B matrix, I need to find B11, B12, B21, and B22. Okay, going back to the equation, first, I'll assume that I1 is equal to 0. So my first scenario is that I1 is equal to 0. So if I assume I1 is equal to 0, then I can calculate B11 and B21. B11 is going to be V2 over V1. And B21 is going to be I2 over V1. For both of them, I have the assumption that I1 is 0. Now for the other two parameters, this time I'm going to assume that V1 is 0. So my assumption is that V1 is 0 in this scenario. Now, if I'm looking for B12, it's going to be V2 divided by minus I1. So V2 over I1 multiplied by a negative sign. And for B22, you need to divide I2 by minus I1. So it's going to be minus I2 divided by I1. Remember that for B matrix, you need to focus on terminal 1 or your input terminal. For these two parameters, you need to have your input open circuited. And for the other two, you need to have your input terminal short circuited. So these two means that you need to focus on short circuited input. And these two means that you need to focus on open circuited input terminal. Okay, now let's look at an example. Let's assume that I have this circuit and I'm interested in a matrix which describes the circuit that I have here between my input and output terminal. So here I have V1 and this is my I1 and this is going to be my I2 and here is my V2 terminal. Now, something that I would like to suggest you is that remember what are the different conditions that you need to apply. So for example, in order to find a matrix, I need to focus on my output terminal. One scenario is that I have to make the output terminal short-circuited, and my second scenario is open circuit output terminal. Now, sometimes short-circuiting or open circuiting make the circuit a lot simpler to solve. So then you prefer to solve two completely separated scenario, one with short-circuited output and one with open-circuited output. But sometimes short-circuiting or open-circuiting really doesn't change too much. Your calculation is not going to be significantly easier by applying a short circuit or open circuit to your output terminal. In that scenario, I recommend solving the circuit in general. So you're solving one time and at the end you can apply your assumption as, for example, V2 equal to 0. Let's see what's going to happen to your final equation. Or I2 equal to 0, and then let's see what happens. So this way you're avoiding 2 times of complicated calculation. I'm going to show you the second approach here. So most of the time when your circuit is a big circuit and you expect to have some difficult solution, then the best solution is solving in general and then applying the assumption at the end, not at the beginning. So here, I'm not going to apply the assumption of open circuited or short circuited output terminal. I'm going to solve it in general. So in general, if I have this circuit, I have to solve with one of the methods that I know. I'm going to choose nodal analysis. So I'm going to make this one my reference, and then this is going to be one node. So I'm going to call it as V1. That's clear why I'm calling it V1, because V1 is the same voltage that I have here. And I have another node here, which I'm going to call it V2. Now let's write the KCL for V1 and V2. So KCL for V1 tells me that I have I1 entering this node. So don't forget about I1, because you don't know what is behind this input terminal. Whatever is attached can apply a current of I1. So I1 is entering, and therefore it's going to be minus. The next component is the current of capacitor, which can be described by Ohm's law. So V1 divided by minus J50. And then V1 minus 5V2 divided by 100. And the last one is the current of 20 ohm resistor, which can be described as V1 minus V2 divided by 20 equal to 0. So this is my KCL for V1 without making any assumption. And for the second node, which is V2, I can say that I have V2 minus V1 divided by 20. That's the current of 20 ohm resistor. Then I have a dependent source current. So the current is described by V1 over 40, and it is going to be positive because it's leaving. So V1 over 40. And then I have V2 over 40, which is the current of the resistor, 40 ohm resistor. And finally, I have I2, which is entering the node, and that's going to be minus I2 equal to 0. So these are two general equations that I can work with in order to find my parameter. Okay, now let's simplify these two equations. I have them here. So focusing on the first equation, I'm going to have V1 multiplied by, so the coefficients of V1 is 1 over minus J50, 1 over 100, and 1 over 20. So if I simplify them, I'm going to have 0.06 plus J 0.02. And then I have V2. The coefficient of V2 is going to be 1 over 20 and 5 over 100. So 5 over 100 is equal to 1 over 20. So we have 2 multiplied by 1 over 20. It's going to be 1 over 10. So the coefficient of V2 is going to be minus 0.1 multiplied by V2. And finally, I have I1. If I show it on the other side of the equation, it's going to be I1 instead of minus I1. So this is my first equation simplified. Let's simplify the second equation as well. Again, I'm going to see what are the coefficients of V1. V1 has minus 1 over 20, 1 over 40. So it's going to be minus 1 over 40. So I have minus 2 over 40, and here it's 1 over 40, so it's going to be minus 1 over 40. And then for V2, I have 1 over 40 and 1 over 20. It's going to be 3 over 40. And finally, I have I2, so equal to I2 on the other side of the equation. I would prefer to multiply everything in the second equation by 40 to get rid of these 40s. So I'm going to write these two equations one more time on the next slide. So these are my simplified equation for KCL that I have for V1 and the KCL that I have for V2. What I did is that I multiplied the first equation by 10, so it simplify a little bit, it get rid of the coefficient of V2, and it makes it easier to work with the numbers that I have in parentheses for V1. And for the second equation, I've multiplied everything by 40, so I have minus V1 plus 3V2 equal to 40 I2. So here I have my simplified equations. Now, in order to find A matrix, I need to apply my assumption. My first assumption that helps me to find A11 and A21 is having I2 equal to 0. And then my second assumption is V2 equal to 0. Let's start with I2 equal to 0. So if I2 is equal to 0, then this term is eliminated. So the second equation can easily describe the relationship between V1 and V2. What is the relationship that needs these two parameters? That's A11. So I'm going to write it here. A11 is equal to V1 divided by V2. And that can be easily calculated from this equation. So if I rearrange this equation, I'm going to have V1 equal to 3V2. So it means that V1 over V2 is equal to 3. So my A11 is simply equal to 3. For the second parameter, what I'm looking for is the relationship between I1 and V2. Remember that we made the assumption that I2 is equal to 0. So this time I have to use my first KCL. In my first KCL, I can replace V1 with 3V2. So I'm going to replace V1 with 3V2. So consequently, I'm going to have V2 multiplied by 3 multiplied by the inside of parentheses. It's going to be 1.8 plus j multiplied by 0.6 and then minus 1 because of this V2 equal to 10I1. Now the relationship that I'm looking for is I1 divided by V2. So I1 divided by V2 is going to be 0.8 plus j 0.6 divided by 10. So I'm going to write it here. So my A21 is going to be 0.08 plus j 0.06. So that's going to be my second parameter that I used the assumption of I2 equal to 0 in order to find it. Now for the other two, I need to go back to my original equation, original KCL and KVL equation. So it means that I have to remove this red assumption here. And this time I need to apply the assumption that V2 is equal to 0. So if V2 is equal to 0, then in my first equation, I can eliminate this term. And in my second equation, I can eliminate this term. So now let's see what I have. In first equation, I have a relationship between V1 and I1. And in second one, I have a relationship between V1 and I2. And let's go back to the equation and see what I was looking for. I was looking for A12, which is described based on the relationship between V1 and I2, and A22, which is described based on the relationship of I1 and I2. I'm going to write them here so I can follow my equation. So my A12 is equal to minus V1 over I2, and my A22 is equal to minus I1 over I2. Okay, so for A12, I can use the second KCL equation because here I have minus V1 equal to 40 I2. So by dividing both sides by I2, then I have minus V1 over I2 as 40. So it means that A12 is equal to 40. And now for A22, I need the relationship between I1 and I2. So in first equation, I have V1 in terms of I1, and in second one, I have V1 in terms of I2. So if I replace V1 in my first equation from here, I can describe my I2 based on I1, and then I can find my constant here. Let's do the rearrangement. So, according to this rearrangement, the relationship between minus I1 to I2 is equal to 2.4 plus j 0.a, which is going to be my A22. Now I'm going to write my A matrix here. So my A matrix is equal to, from the first scenario, I had A11 as 3 and A21 as 0.08 plus j 0.06, and my A12 from second scenario is equal to 40, and my A22 is equal to 2.4 plus j 0.8. Again, you can see that these two are not equal because I have dependent source in my original circuit.